Welcome to the introduction video of the Gresty Academy crash course into volumes bounded by surfaces. And what we're going to do is we're going to do the introduction by answering this question here, which is about as standard as it gets. What you have is you have to find the volume of a solid bounded by these surfaces here. Y equals x squared, y equals 2 minus x squared, z equals 0, and z equals y plus 4. And one of the hardest things about this is actually imagining what on earth it is that this volume looks like. So let's have a quick look here. This is courtesy of desmos.com. I'll just have to change the colour. Let's go for yellow, just so we can see what's going on here. Okay, so basically here we have obviously the y-axis, the x-axis, and the z-axis here. So this one here is y equals x squared. The blue one is y equals 2 minus x squared. Clearly the xy plane is z equals 0, and then this green one here is the plane z equals y plus 4. And what we have therefore, the bounded bit, so we have this bounded bit here, and then it's bounded by the z equals 0, i.e. the xy plane, and it's also bounded by this plane here. And so the volume that we seek is basically that bit there. Okay, now before we go into the details, let's just go back into our favourite black pen. Before we go into the details, let's just have a quick look at single integrals, just very, very briefly. So if we have, let's just say here, we have a single integral here, x and y. We're only dealing with the x and the y plane here, and we have some function here, f of x, y equals f of x, and we wanted to find the area under that curve. Well, basically what we would do is we would draw a little rectangle there, dx, and the height of that would be f of x, and then the area of that rectangle would be f of x times dx, and therefore the integral of the whole area would integrate from the beginning of the x to the end of the x, so the integral would be from x0 to x1 f of x dx, i.e. basically just summing up all of the areas of those rectangles. And basically what we do with the volume is we just extend that to 3 dimensions instead of 2. Okay, so basically what we're going to do in theory, we have our x, we have our y, and we have our z. And I'm just comparing this to the two-dimensional. So in the xy plane, we have some sort of area here. And what we're going to do is we are going to crisscross this area like this, getting a load of little squares, which are dx times dy, and then our z up here somewhere, we are going to have some surface, and what we're going to do is we're going to build the cuboids, a little bit like the skyline of Manhattan or Singapore or something like that. We're going to build all of those cuboids, and each one of those cuboids is going to have a volume of this bit here, which is z, which is f of xy. So it's going to be f of xy times by dx times by dy, each of the little cuboids. And then all we're going to do is, just like we did here on the single integral, we are going to sum all of those over x and over y. And so basically our volume will become this double integral here. So let's go on the actual question at hand, and that hopefully will make it all a little bit clearer. Okay, so basically we have, let's just look at the xy plane first on this question. So we have y equals x squared here. That's y equals x squared. Here's obviously x, and here's y, and z will be coming out of the video, but we don't need z quite yet. And this here is y equals 2 minus x squared, and so this bit is going to be the area in the xy plane about which we are going to integrate, and then the z comes out. So what we need to do first of all is we need to find out what these intersection points are. Well, basically that's when x squared equals 2 minus x squared, i.e. when x squared equals 1, i.e. x equals plus or minus 1. So those 2 points there are x equals minus 1 and x equals plus 1, and so they are going to be our limits of integration for x. So that's quite easy. Now let's just redraw this. again. So basically it's here's y equals x squared, and here is y equals 2 minus x squared. So we know that this point here is minus 1, and we know that this point here is 1 on the x. And so basically our integral will be from minus 1 to 1 on the x. Now what about y? So y, we will enter at this point here, and we will exit at this point here. And when we do that across from minus 1 to 1, we will have covered the entire area that we need to integrate. So basically this will be our x integral, and then our y integral, we will enter at x squared, and then we exit at 2 minus x squared, and that is our y integral. So now what we can do is we have our x and our y, and then all we need to do is multiply that by f of x of y, and then dy dx. And once we've got that, we have our double integral. So we know that f of xy from the question, f of xy, i.e. z, was equal to y plus 4. So basically we now have our double integral, which is that the volume is equal to the integral between minus 1 and 1, that is the x, the integral between x squared and 2 minus x squared, that is the y, and so these two integrals between them calculate that area there, and then we multiply by the height, if you like, of the cuboids, the height of the towers in Manhattan or Singapore, y plus 4 dy dx. So that is the volume of each of the cuboids, and then when we sum them over x and y over that area, that gives us the entire volume bounded by our surfaces. And by the way, at the end we're going to just come back to this, so just remember that one. But let's now do this double integral, which is going to give us our answer. So basically the first thing we do is we do that integral there. So our volume is equal to the integral between 1 and minus 1 on the x, and we can do the y integral now. Well, the integral of y plus 4 dy is y squared over 2 add 4y between 2 minus x squared and x squared, and then we've got to do the integral afterwards with respect to x. Okay, so that equals the integral between 1 and minus 1. Okay, well, so basically what we've got to do now is we've got to put 2 minus x squared in and then x squared in, so that gives us 2 minus x squared over 2, add 4, 2 minus x squared, minus, putting x squared into there, x squared over 2, add 4x squared, and all of that lot will then be integrated with respect to dx once we've sorted it all out. So that equals just taking the half out, half integral between 1 and minus 1 and expanding all of these things out. 4 minus 4x squared, add x to the 4, add 16 minus 8x squared, minus x to the 4 minus 8x squared dx, and the x to the 4 cancels, making things slightly easier. So that equals half the integral between 1 and minus 1, adding everything up, 20 minus 20x squared dx. So that equals half. We can now do the dx integral, half 20x minus 20x cubed over 3 between 1 and minus 1. I'm just being slightly careful with our signs. That's 20 minus 20 over 3 minus 20, add 20 over 3, which equals a half 40 minus 40 over 3, which equals 40 over 3, which hopefully is one of our answers. Yes, it is. Hey presto, answer D. Okay, so that is how we do that question there. Now what I'm going to do is I'm just going to return to where was it? I said I was going to return to here. Right, okay, so just remember that. There's a different way of doing it, and some people find this third way more instructive. So what they basically say, and it is the same thing, you'll see in a second. So here's the x, y and z, and basically we have some sort of area here on the xy plane, and then of course we have it going up to some plane up here in the z. But what they say is, okay, well, let's take a little cube somewhere inside which has dimensions dx times dy times dz, And then what we will do is we will integrate over the x and over the y and over the z. So we'll actually do a triple integral. So the triple integral would be the integral over x, the integral over y, the integral over z of dz, dy, dx. That would be the volume, and there's nothing wrong with doing it that way. And in fact, for some people, it's actually a lot clearer if we do it that way. And so what we would have in this particular case then is we would again have the limits for x would be the same, minus 1 to 1. The limits for y would be the same, 2 minus x squared to 2 minus x squared. Now the limits for z would go from z equals 0. Remember that the lower bound of the z was z equals 0, which is the xy plane, up to z equals y plus 4. dz, dy, dx. And then what we do is we integrate the inner of the triple integrals, and well, that would be equal to the integral between minus 1 and 1, the integral between 2 minus x squared and 2 minus x squared, sorry, and that would be z between y plus 4 and 0, dy, dx. And of course that there is equal to 1 and minus 1, 2 minus x squared, well, that equals y plus 4 dy dx, which gets us right back to this point here. So it's exactly the same, but some people do prefer to do the triple integral because it just seems a little bit more intuitive as to exactly what we're doing. And we are clearly finding the volume here by finding this little cube and then multiplying it out x and y and z. Okay, well, I hope you found this introduction useful. So there'll be more videos in this podcast series. They will really begin to start looking at exam techniques and tricks as to how to solve these quicker. Hope you found this useful. If you have, please like this video and subscribe to the Gresty Academy YouTube channel. Thank you.